All right, welcome to the explainer. Every time you turn the key in your car, you're basically in command of thousands of tiny controlled explosions happening every single minute. But how in the world does all that chaos create smooth, powerful motion? Today, we're going to pop the hood and look at the fundamental physics that turn hot gas into actual horsepower. So let's dive right in.
When you really get down to it, every engine is trying to solve this one big puzzle. How do you take something you can't even see, a puff of hot gas, and turn it into the raw physical force that can move thousands of pounds of steel down the road? That's the mystery we're going to unravel today.
Okay, so it all kicks off with this incredibly fast, violent push. You've got your fuel-air mix, it ignites, boom, and that super hot expanding gas just slams into a piston. That single initial force is where all the engine's power is born, and in physics, it has a very specific name. So, that push, it's got a name in physics, of course. It's called moving boundary work. And it's pretty literal. The boundary is just the top of that piston, and the work is that useful force it creates when it gets pushed. This one little action, happening over and over, thousands of times a minute, is what generates all of an engine's power. Okay, so how do you actually measure this stuff? Well, the cool thing is, the basic idea is beautifully simple. Work is just the pressure of that gas multiplied by how much the volume changes. So when the gas expands and shoves the piston down, it's doing work for us. But when the piston has to move back up to squeeze the next bit of gas, that takes work. We have to put work in. Now hang on to that idea, because it's going to be super important in just a minute. Right, so obviously engineers can't just wing it here. They need a way to actually see what's happening with that work. And to do that, they've got this awesome tool that's, well, it's kind of like a work map for the whole engine cycle. And that map, we call it a PV diagram. It's a graph, simple as that. You've got pressure going up and down on the vertical axis and volume going side to side on the horizontal one. As the engine goes through its cycle, we can trace a path on this map that tells the whole story of what that gas is doing, when it's being squeezed, when it's expanding, all of it. And this is where it gets really cool. This is the big aha moment of this whole map. You see that area under the curve we trace? That's not just some abstract shape. That is the work, literally. A bigger area means you got more work out of it. It turns this really complex, high-speed process into something you can just see and measure visually. It's an incredibly powerful tool. Now, this map shows us something that is absolutely critical. And it's that work is path-dependent. What that means is it really matters how you get from point A to point B. So look at this. On path A, the gas expands while the pressure is still super high, and boom, you get 10 kilojoules of work. But on path B, you let the pressure drop first, and you only squeeze out 5. This isn't just some minor detail. Figuring out how to take the best path to get the most work is the secret to making an engine powerful and efficient. But none of this is just happening randomly. The whole thing is playing by a very strict set of rules. And the ultimate rule book for all energy, whether we're talking about an engine, a distant star, or even our own bodies, is the First Law of Thermodynamics. You've probably heard this one before. It's maybe the most famous rule in all of physics. And what it really boils down to is a simple, unbreakable accounting principle. You can't create energy out of thin air, and you can't make it just disappear. All you can do is move it around or change what form it's in. Okay, probably the best way to wrap your head around the first law is to think of it like a bank account, but for energy. Any heat you add to the system, that's a deposit. Any work the system does, like pushing that piston, that's a withdrawal. And any change in the energy stored inside the system itself, well, that's just the change in your account balance. So all of that gets boiled down into this famous little equation. Q minus W equals delta U. Q is the heat we add. That's our deposit from the burning fuel. W is the work the engine does. That's our withdrawal that pushes the car forward. And whatever's left over, the difference between the two, is delta U, the change in the system's own internal energy. It's what's left in the bank. Okay, so let's break down those 3 parts of the equation a bit more. Heat, work, and internal energy. I like to think of them as the 3 different currencies of energy. So first up, you've got heat, or Q. That's just energy moving around because of a temperature difference, always from hot to cold. Then you've got work. W, which is energy transferred by a force, like that piston pushing down. And finally, there's internal energy, U. This is all the energy that's just stored inside the system, locked away in the jiggling and buzzing of its molecules. Heat and work are energy on the move. Internal energy is energy in storage.
All right, we've got the push. We've got our map. We've got the unbreakable rules of energy. Now, let's put it all together and see the magic happen. Let's find out how an engine actually makes useful continuous motion.
So here it is, the real secret sauce of an engine. See, an engine runs in a cycle, over and over. And for that cycle to actually do anything useful, the work you get out when the gas expands has to be more than the work you have to put back in to compress the next batch of gas. It's just like running a business, right? Your income has to be bigger than your expenses. You need to make a profit. In an engine, that energy profit is what actually moves the car. Let's put some real numbers to this to make it clear. So, let's say during that power stroke, the expanding gas does 10 kilojoules of work. That's our income. But then, the engine has to use some of its own energy, let's say 3 kilojoules, to compress the next bit of fuel and air. That's our expense. So what's the bottom line? 10 minus 3, you've got a 7 kilojoule profit. That's your network. That's the good stuff. And you know what? If we jump back to our PV diagram, that work map we talked about, this network has a physical representation. It's the area that's completely enclosed by that repeating cycle loop. That area inside the loop, that is your network. That is the prize. That's the useful energy that overcomes friction, pushes through the air, and ultimately turns the wheels and makes the whole thing go. Okay, so let's do a quick recap of the big takeaways here. You've got boundary work, which is that powerful push from a gas on a piston. You've got the PV diagram, our map, where the area tells us how much work we've done. You've got the first law, the universe's non-negotiable energy budget, and all of that comes together to give us network, the useful energy profit we get from a cycle that powers our world. And the amazing thing is, this law isn't just for car engines. It's happening inside you right now. The energy you get from that sandwich you ate for lunch, that's your heat in. Every step you take, every time you lift something, that's your workout. So the next time you start your car, or even just go for a jog, you're literally watching the first law of thermodynamics in action. My question for you is, where else do you see this universal rule hiding in plain sight? Thanks for tuning in.